Okay, here are the Chapter 14 notes. Section 14.1, Basics of Solutions. This whole Chapter 14 is on solutions, which are homogeneous mixtures. Homogeneous mixtures of one or more solutes and a solvent. The substance that gets dissolved is the solute, and the substance that does the dissolving is the solvent. And the solvent is usually the substance present in greater quantity. Zoom this in just a little bit. There. That should be a little easier to read, I would think. Okay. And we can measure the amount that a given substance will dissolve into a solvent at a given temperature. That measurement is known as solubility. We kind of explored this a little bit in our chapter where we're talking about double displacement reactions. If a substance is soluble, highly soluble, in a solvent, we can dissolve large quantities of it if the substance has low solubility. We cannot dissolve much, and if a substance is insoluble, it cannot be dissolved at all. Solubility changes with the substance and with the temperature. And we'll discuss that more in 2 minutes on the top of the next page. We'll get more specific on how it affects solubility temperature. Solutions can be made out of any phase of matter, solid, liquid, or gas. We kind of talked about that again in way back, chapter number 1, 2, somewhere back there. But if we have, for example, the air in our room, that is considered to be a solution, a mixture, a homogeneous mixture of gases. We can get more specific talking about liquids. We have a couple specific terms here that are addressed just for liquids, though, and that is that if one liquid is capable of dissolving another, we say that the liquids are miscible. An example of this might be, if you've ever gotten one of those frozen orange juice concentrates and mixed it with some water, you were able to generate this kind of homogeneous solution on the end. Well, if you had non-pulpy, anyway, it would be fairly homogeneous. Orange juice concentrate and water. If the liquids are not capable of dissolving each other, we would say they are immiscible. And an example of that would be oil and water mixture, like we have. Excuse me. Like we have in our classroom. There are a number of factors that affect solubility, and number one among those is polarity. We say often that like dissolves like. Polar compounds dissolve in polar solvents, and nonpolar compounds dissolve in nonpolar solvents. Water, being a polar molecule, does a really good job of dissolving other things that are polar and or ionic. And that means water dissolves a lot of stuff, because if you look at the periodic table, most elements are metals, and so most compounds are ionic or at the very least polar. But there are things water can't dissolve, like oil, and oil could therefore would be dissolved into a non-polar solvent. So if we can't dissolve something into water, we would probably try an oil base to see if we could dissolve it into that. Solubility is affected, as we said earlier, by temperature. This one's a little bit tricky because it works differently for solids than it does for gases, and that being that if the temperature increases for solids, the solubility will increase. So if we want to dissolve some sugar, it's going to dissolve faster in hot water than in cold. But it decreases with temperatures for gases. And this is both a good thing and a bad thing when it comes to, say, the natural world around us. For example, this ability of the water to store more oxygen as it gets colder is one of the things that allows fish to winter over in lakes that freeze completely over the surface. That water is holding a higher percentage of oxygen. As it's cooling down, it's absorbing more and more oxygen from the atmosphere before it freezes over, giving this kind of reserve battery for the fish to live off of. On the other hand, if the water gets too warm, and especially if we get something else competing for that oxygen in the water, like an algae bloom, then we can actually get a fish kill. Because the water, as it's warming up, can hold less and less oxygen as it is, and if we get a competitor consuming some of that oxygen, the fish can, suffocate to death. There are some factors that increase the rate of dissolving. First off is that the surface area. Solids can only dissolve at a surface that is in contact with the solvent. So if you throw a big hard chunk of sugar into your pitcher to make your Kool-Aid with, it's going to probably not dissolve as well as if you had it finely ground up, if you had the normal kind of ground sugar, because that block has a lot of sugar molecules on the inside of it that aren't immediately exposed to the water. The water can only dissolve the sugar on the outside of that block. Whereas with the small grains, there are less molecules being hidden in the center of them. More of them can be exposed to the water, and therefore they can dissolve more quickly. So we can increase the surface area by grinding or smashing a solute. Kind of smash it into itty little pieces. That maximizes the surface area. With temperature, we just talked about up here that temperature can affect solubility. It can also affect the rate of dissolving. And for a solid, it would increase almost all the time. Increases the rate. And even for gases, even though the substance can hold less gas, it does still tend to dissolve more quickly because, the molecules are moving more quickly. So they hit each other more often and can kind of get stuck to each other and distributed evenly. The solute concentration is important. The rate of dissolution slows down as the solution approaches the saturation point. And finally, we all know this, again, from making Kool-Aid or something similar. Hopefully we all know this, that stirring a solution would speed up the rate of dissolution. Speeds, 2E's, speeds up. And we want to get our sugar into our Kool-Aid faster, we stir it. Okay, that is it for the videos for section 14.1. We'll be back with 14.2 shortly.